So you guys have you've done some reading. You've read like chapter 4, right? Learning about essentially what forces are, types of forces, things like that. There's the basics of here are Newton's 3 laws. And you also did a PhET that had to do with the interaction between force and mass and what the outcome is that dependent variable of acceleration. So we're gonna go through like essentially just quickly what forces are, what happens, right, and then what Newton's laws are to get an idea of all that. So force is really there's a definition, but it's almost like a 3-pronged definition. Okay, and as we move on and we go through the definitions, they change or they become a little more from simplified to more complex, and you get a little more technical about it. So the first one for force is that it's just any push or pull. So anytime you act on something, right, anytime you push something, you pull something, you're applying a force, right? Very simple, makes sense. Okay. Now, the next one you saw, right, you read about and you saw firsthand in that PhET, that 1D motion PhET, was that it's a cause of acceleration. So anytime you push or pull on something, you're going to cause it to accelerate. Simple, right? So anytime you do something, you apply force, you're going to cause it to either speed up or slow down or change its direction. Okay? And the third one is that it's an interaction between objects. Okay, so those are the 3 big things that anytime there's a force, it's going to be a push or pull, it's going to cause something to accelerate, and it has to be an interaction between 2 things. Okay? At least 2 things. I think the first 2 are pretty obvious. You've seen. This third one is a little bit interesting, all right? Like, I'm leaning against the board. Interaction, right? I'm applying a force to the board. The board's going to apply a force back to me, right? So there always has to be a pair, right? Forces then have to come in pairs, right? You'll never have a force, like a single force, by itself. Impossible, right? So if you can imagine, Dan running around swinging his hands in the air, look, I'm applying forces. Maybe technically yes, but no. Okay? Not until one of his hands connects with someone or a wall or a locker or something, right? That's when there are forces then being applied, right? Then all of a sudden we have a force. Because we need 2 objects to interact with each other in order for that to occur. We could say technically, yes, he's applying a force because his hand is interacting with air molecules and the air molecules are then being moved. But in physics, a lot of physics, we like to neglect that there's such thing as air. So we just live without it. So, but it's very important that we've got these 3 things that define forces. Okay? And really, when they all go together, so it's not like, okay, this is the definition I'm going to use for this problem, this is the definition I'm going to use for this problem. They all come together, right? They're all wrapped up in one package. Okay? Now, there are many types of forces, really, because again, there's many different ways that we can cause something to accelerate. And the book gave you some of the definitions, and we're going to go through some of them, but realize that while they have specific names, some of them have specific names, they're all just forces. Okay? When it comes down to it, you treat them all the same way. They may have a different name for some of them, but they all interact and they all work the same exact way. Okay? So the first type we got all these different types of forces. Let's look at them. See what happens. All right? The first one that we may have is weight. Okay? So in weight, very simply, weight has to do with your mass. Okay? You may say if you weigh something or if you have weight, it's from your force of gravity. Okay? And that's true. Gravity is what creates your weight. Okay? It's the force of the earth pulling down on you. Okay? But it is dependent on your mass. Right? So we may call it F sub g. Right? Force of gravity. And so this is your weight. Force of gravity is equal to then your mass times the gravity. Okay? Weight is something that is derived. right? Weight is dependent on gravity. Mass is that constant thing, right? Because remember, mass is just the amount of stuff that makes you up. It's right? The amount of matter you have, right? All the molecules in you that when you stick them all together into one volume, right? And that is then your mass, okay? And the only way you can change your mass is by losing some of those molecules, okay? Whether it's working out, eating less, losing a limb, any of those things will cause you to change your mass, okay? And you can also gain mass by maybe being a little lazy and hanging out in front of the TV and just pounding burgers all day long. That'll happen, okay? So, if you look here, right, for all intents and purposes, right, this mass isn't changing. So the only way you can change your weight is by changing gravity, okay? And that's only going to happen if you leave this planet, right? You go to the moon, the gravity on the moon is 1/6 that of Earth. So you take your weight on Earth, you just cut your weight down to 1/6 by moving to the moon because of the change in gravity. What's that? We'll do that, all right. Now if you go to Jupiter, which is about 3.5 times the force of gravity, right? It's about 35 meters per second squared. You now have gained 3.5 times the weight. Okay? Now here's the interesting thing though, right? You still have the same mass. Your mass has not changed, whether you're on Earth, the moon, Jupiter, any place you can think of, right? If you go to an asteroid, whatever it may be, okay? You still have the same mass because you still have the same amount of molecules that make you, okay? Only thing that has changed is gravity, all right? So that's weight. So we're going to talk about free body diagrams. Weight is always the easy one, all right, that you got to get. So your next one that you may see is friction. Why did that do that? All right, and friction is the interaction between surfaces of two objects, right? If you were able to get like a really good microscope, almost like a scanning tunneling electron microscope, so you could see like really, really, really close, right? You would see the bumps in surfaces, and friction occurs because the bumps in the two surfaces block into each other, right? And they apply force on each other, and that's what causes friction, right? And the smaller those bumps, right, the smoother the bumps, the less friction there is, right? Because there's less of those, like almost like little Velcro things to grab onto each other. Whereas if it's very rough, right, now those bumps become bigger, and now they really lock in and they hold on to each other, okay? There are two types of friction, right? Before we get to that, actually, if I want to know what friction is, it's going to be equal to this thing called mu times the normal force. Okay? The normal force we'll get to in a second, all right? But this thing mu, it's like a U, almost like a cursive U kind of thing. It's a Greek letter mu, Greek letter really for U, kind of, right? And it's a constant. This is a number that is given to you, or you look it up in a book, right, in a chart, or they give you enough information that you have to then solve for it, okay? There are scientists and there are people that literally, usually are some sort of lab tech that is usually given, all right, here are a bunch of different things. I want you to tell me what is the coefficient of friction between all these different things, okay? And that's how they get in a chart. That's how they get in a book. And it's dependent on whatever the materials are. So there could be, wood on concrete, wood on rubber, wood on, anything else, wood on plastic, right? And they just go through the tests and they determine what these things are. So it's very dependent on what the objects are. Now there are two types, okay? You have static friction, right? Now static friction occurs when the object is not moving, okay? Does that make sense? So static friction, static means not moving, right? Happens when the object is not moving, okay? And then there is kinetic friction. Kinetic friction occurs when you are moving. Okay? And as soon as you start to move, right, so you're not moving, static is there. As soon as you overcome this static friction, kinetic friction then takes over. Okay, does that make sense? All right. Now here's the very important thing. You can see here that friction depends on the coefficient of friction in the normal force. Well, when you're pulling on something, right, when you're applying a force on something, you start with static friction, and as soon as it starts to move and you overcome the static friction, you're now moving, you now have kinetic friction. The only thing that can change of these three things is going to be mu. Between these two things, the coefficient of friction is going to be the only thing that changes, all right? And it's going to take more force to overcome static than it will be to keep it going once kinetic is involved. So something that is very, very important is that the coefficient of friction for static friction will always be greater than the coefficient of kinetic friction. And it should be a number less than 1. Every coefficient of friction is less than 1. Okay, so it's point something. Technically, right there is no friction because there's no force being applied to it to try to move. But as soon as you start to pull on it, right. And there's not a lot of friction between that because you're very easily moving it. Now, if we're talking about trying to move my desk, that's a different story. Okay? Yep. Static friction, imagine pulling on the table and it's not moving. So you're applying a force, you're pulling on the table and it's not moving because all the force that you pull on it to move this way, static friction is pulling it the opposite direction. Okay? But then once you get it going, now your force is greater than the kinetic friction moving the other way. Okay? Why is mu static always greater than K? Because it takes a greater force to get this going, right? To break it. Then, you ever notice when you pull on something, it's really hard to get it going, but once it's going, it's easier. Right, from moving, right. Okay, so there's some dams that are called gravity dams, right, that hold back water. And they are all built on static friction. They just make them so big that there's a massive amount of static friction, and that's how they hold back the water.
So does that kind of depend on mass?
Because normal force is going to depend on usually, 97% of the time it's going to depend on the mass. Okay? Where am I? Come on, what are you doing? The next type that we may see, or that we will see, is drag. Drag, they talk about drag in the book. We'll talk about it in name as just like, all right, this is drag, but there's nothing we're going to calculate. Drag has to do with air resistance. All right, so drag comes from, air molecules hitting an object as it moves. Very simple. No, the pen was just not agreeing. You can see what's going on. Okay? No drag. No drag. So if air resistance is negligible, there's no drag. Because it's essentially drag is another name for air resistance. Similarly, you may see thrust. Thrust, very simply, is just a force that is propelling an object forward. All right, so thrust may be a rocket, right, pushing a shuttle somewhere, right? That is thrust. What happens with thrust usually is that some sort of, you get like hot gases, I think of like a rocket, applying a force to the air, and the air is then pushing the rocket there. Okay? Yep.
Is it like up or like forward?
Which one? Doesn't matter. Because thrust can come from a plane. So if you're talking about thrust in a plane, it's the propeller acting on the air molecules, and the air molecules then acting on the propeller. Yes. Yes. Well, no. You could be moving in one direction, and you could have thrust slowing it down. Right? Not in the technical sense of the definition, no. Okay. Usually thrust comes from air molecules being applied to an object. Yes. That would be, I guess you would call that thrust, yes. Okay. Colin. Okay. The normal force is our next one, and this is an important one. If there are three super important ones, it's friction, it's normal, and it's weight. The normal force, all right? The normal force is a force that is supporting an object, all right? So think of it this way: as if, like your book sitting on a table, it has weight because it has mass, right? And weight is dependent on mass. So there's weight pulling the book down, right? Well, clearly the book is not moving, so there needs to be some other force supporting it. Okay? So in this case, it is the table supplying a force upwards to counteract that weight. Okay? The name we give that force that is supporting the weight of the book, we call it the normal force. Okay? Yep.
Is the normal force that back around the book
Yep. Okay.
So if you have something like pressing down on the table, the normal force is resisting the down force?
Correct. Yep. Yep. And this is super, 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 super important. And this is going to be come up big next week. Weight always goes straight down. No matter what happens, weight is always straight down. Okay? Now, we'll say that normal force is always perpendicular to the surface. Okay? So weight is always straight down no matter what happens. The normal force is always perpendicular to the surface. Okay? So if this is your surface, here's the normal force, right? Perpendicular. This is your surface and there's an object on it, this is weight. Okay? If we put it on a ramp, right? Like this, on a hill, weight still goes straight down. Correct? Normal force still now is perpendicular, so it's now at an angle. Okay? And that makes a difference. That makes a very big difference. Okay? And we'll talk about that next week as we move forward in what they call applications of Newton's laws. Okay? So these are some important forces. These are all forces. They just kind of classify them with specific names. Okay? There are other forces, right? We have tension, right? Again, it's a force. They just call tension then, a force that's in like a string or a rope or a chain, something like that. Okay? They have the spring force, which is a force from, a spring acting on an object. All right? There's the electromagnetic force that has to do with clearly electricity and magnetism, which we won't get into electromagnetic force in this class. It's just not part of the view of this class. So there are all these different forces. The important thing, again, with all these is to realize that they are all forces and they all follow these three definitions. Okay, no matter what, they all follow these three definitions. No matter what the name is. Okay? Some of them may have, specific equations that go with them, but they all are a push or a pull, they all cause acceleration, and they all are interaction between objects.